So, can you hear me? Yeah? Good. I'm, as you probably know, I'm Gert de Cooman, and this is you. This is you before the quantum lecture. There's a very good reason why we took this picture before lunch. Because the organizers and I, we thought it would be a good idea to hit you when you're at your weakest. After lunch, after 4 days of lectures, we decided to give a quantum lecture. Now, I'm extremely nervous for this, because I don't know how much you know about quantum mechanics. Has anybody had any experience with quantum mechanics before? Ugh. Okay. The easier question, does anybody know anything about linear algebra, matrices? Ah, that's better. Yeah? I could. Is that better? Okay. Fine. So yeah, that reassures me a little bit. But the program for today is this. I'm going to start with the red part, and that is imprecise probabilities the way I see it. But then I'm going to abstract away from it, right? I'm going to make it extremely abstract. Why? Because in abstraction is generalization, and that means that we will have a theory that has the bare bones structures of what we need, and then we can apply that to whatever we want, right? So after we've done that, we'll apply it to classical probability, and we will recover classical probability. That will be the easy part. That's probably going to be like the first hour, hour and a half of the lecture. And then I'm going to move to the orange part and the yellow part, and I'm going to try and make sure that you, together with me in this lecture, discover that if you do this, the exact same thing almost, the exact same ideas, you get quantum probability. So that these are just two sides of the same thing, actually. Whereas I think most of the time people tend to say that quantum probability is quite different from classical probability. What I'm going to say today is that it isn't. All right? So that will be my main message. Right, so let's begin with this imprecise probabilities on normed real vector spaces. I often do this. I give a picture of the pioneers. The original pioneers are here. Peter Williams, Peter Wally, and Teddy Zeidenfeld. So I'm going to talk about desirability in the beginning. People who also worked on desirability are Serafin Moral, Enrique Miranda. Some of you know Enrique Miranda. Marco Zafalon, Erik Quagbuur, who was also here, and then me. So let's begin with the basic idea. We're going to talk about abstract rewards. So we have rewards, and they are abstract things. I don't want you to. The only idea is that they are uncertain rewards. Yeah? And I will call these uncertain rewards options. And you, and by you I mean some abstract decision maker, could be you. You will have to express preferences between these uncertain rewards, because it could be that you prefer one uncertain reward over the other. Right? Now, a crucial property of such uncertain rewards is that you can add them. You've seen that in the first lecture. You can add uncertain rewards, then you get the combined outcome of them, and you can multiply them with real numbers. You can scale them if you want. So they live in a vector space, right? So we will live in a vector space. We have a vector space U that we will call the option space. It's a real vector space. I'm not saying anything else. Okay. And then you come in. And you express your preferences between options. So I have an option U and an option V. And I express that you think that U is strictly better than V. And I will explain later what strictly better means. So you strictly prefer U over V. And we will denote this by this U little triangle V. Okay, you'll probably quite used to the fact that at some point we introduce rationality criteria. And these are the basic properties that I'm going to impose on these preference relations. So this little triangle is a preference relation, and I'm going to require that it is a strict partial vector ordering. So it's strict, which means, yeah, it's a strict preference, which means that it is irreflexive. Irreflexive means that no option is strictly preferred to itself, right? And it's also transitive. And transitivity is typically a property that we require of preference. So there's nothing very strong there. The second one is that this preference relation is compatible with the vector ordering, in the sense that if I have one option that is preferred to a second one, then adding the same vector to two sides of the inequality preserves the inequality. And the third one is that it is compatible with scalar multiplication. So if I have a real number that is positive, positive mind, then multiplying both sides of the inequality with that positive number will not affect the preference. Yeah. So these are, in essence, these are linearity properties. They express, in a sense, that the uncertain rewards that I'm using are expressed in terms of a utility scale that is linear. Yeah. And then there's the last one, and that is the important one for this lecture. That is, there is, in the background, some other vector ordering. And I will note this other vector ordering by this curly preference symbol. And the first axiom says that if U is preferred to V in the background, then U must also prefer U to V. And by background, I mean that this is a preference that is always there. Even if you have no other preferences at all, it should always be there. It's something that expresses beliefs, preferences, that even when you're not thinking or believing, should be there. So it represents, if you want, complete ignorance or complete lack of conviction. That's what this background ordering represents. Right? Again, this is a partial order, not a total order. Right? We allow it to be a partial order. Okay, everything is with me? Everybody's with me at this point? Yeah? Right, now, because of the they are, in this point, I can't say anything more, it's just abstract, right? I'm just trying to abstract away what they are. When the options are gambles, this is what you've seen before, when these options are gambles, then this ordering is just the Pareto ordering. Yeah, typically. That's what I represent by complete ignorance, or complete nothing, knowing nothing. That's what's always there, right? If one gamble always gives you a higher reward than another gamble, then you should prefer one over the other. Yeah? But this here is abstract. I'm just taking another ordering, and it's always there. And I call it the background. Okay? Right. Then, the cool thing about these strict preference orderings is that they can be completely characterized by the ordering with respect to 0. So the idea is, let's look at all the options, U, that are strictly preferred to 0, where 0 represents the status quo. You get nothing. Your capital doesn't change. Right? And so you look at all the options that are strictly preferred to the status quo. And I will collect all these options in a set. Typically, I will denote that set by D. And I will call this D your set of desirable options. They are the ones that you find desirable because you prefer them to nothing. Right? And this set, interestingly, completely characterizes the ordering. Because look at this chain of equivalences. If U is preferred to V, I can add minus V to both sides of this inequality. So I get that this is equivalent to U minus V is strictly preferred to 0. In other words, U minus V is in D. So if I know D, I know the preference. Yeah? So working with a set of desirable options or working with the preference ordering doesn't matter. It's the same thing. Okay. So this is your set of of desirable options. Now, I had these 4 criteria for rationality for the preference ordering. I'm now, because of the equivalence, I can turn them into 4 criteria of rationality for this equivalent representation, namely your set of desirable options. The fact that I have a strict ordering is represented by the fact that 0 is not desirable. You cannot prefer 0 to itself. Strictly prefer 0 to itself. So 0 is not desirable. One thing. The 2 linearity requirements, the fact that I can add that this ordering is invariant under addition and positive scalar multiplication, turns into D2 and D3. So if I have 2 desirable options, then their sum is desirable. And if I have a desirable option, then multiplying it with any real number that is strictly positive preserves the desirability. And then finally, the background, of course. Right? We need the background. So if you prefer, or if an option is preferred in the background to 0, then you must also prefer it to 0. Okay. So in summary, your coherent or a coherent set of desirable options is a convex cone. Why? D2 and D3 are just the convex cone properties, right? It's closed under addition and under positive scalar multiplication. It includes what we call the positive convex cone, and that is this set. This is the set of all the options that are positive, greater than 0 in the background ordering, right? This one. This is what we call the background cone, or the background convex cone, the cone of all the positive options in that background ordering. And so, if your option is in the background cone, it must also be in this cone. So the cone must include the background cone, and it can't contain 0. So you've seen pictures like this before. This is in 2-dimensional space, where this is the background cone, so everything that is here is the background cone. This is a possible set of desirable options in such a space. So it cannot be in the red zone. Yeah? So points in this 2-dimensional space are options. They cannot be in the red zone. They can't be 0, but they also can't be here. Why not? Why can't they be here? I haven't said that they can't be here in those axioms. It's a consequence of the axioms. Why? So take an option here. This is negative. So take the opposite one here, the additive inverse. That will be in the positive cone, right? It's going to be desirable. If this is desirable and this is desirable, their sum 0 should be desirable, which it isn't. So this is forbidden as a consequence of the axioms. It's not explicit in the axioms, but it's implied. Right? Okay. So yeah, that's it. Looks like this. Another interesting thing, the difference between these 2 boundaries, because these are boundaries, the difference between them is that this boundary is included, which is why it has a full line, and this boundary is not included. Yeah? So if I take a point on the if a point is on this boundary, then all of these points on this boundary should be there, right? But it's quite possible, compatible with the axioms, that I can take something here on this boundary that is not inside it, and then none of these points is inside it, by this axiom. Okay? So it's possible to have open boundaries in this theory. Something you should remember. Okay. So this is what we call coherent sets of desirable options. It's an abstract version of the coherent sets of desirable gambles. And there is one property, and now I'm going back to the talk that Alessandro was giving on the second day. Interesting thing is that desirability, this notion of coherence, is preserved under taking arbitrary non-empty intersections. That means that if I have a collection, a family of sets of desirable options that are coherent, so I take a family, these are coherent, then their intersection will also be coherent. Why? Because the desirability properties are typically preserved. I'm going to give you one example. Suppose that U and V are in the intersection. This means that for all I, U and V are in the I, right? That's by definition of the intersection. So the sum will be in the I, and therefore, because this is for all V, the sum will be in the intersection. Okay? So this additivity axiom is preserved under taking arbitrary intersections. All right. Now, this is important. Why? Because this intersection property is what in mathematics is behind the notion of closure. This is what is behind topological closure. Any type of closure that you know is this intersection problem. If something is preserved under taking intersections, then we have closure. I'll explain you why. Okay, let's begin. We're going to do a little bit of logic here. This is why I was talking about what Alessandro was talking about. There's a notion of consistency. So what I've drawn here, the golden dots here, are options. And these are things that you have said to me. You've told me these things I accept. These things are desirable to me. We call this an assessment. So this is a set of options that is an assessment. This is what you give me. And then what I'm going to try to do is draw inferences from this. I'm going to try and find out whether other options are then also desirable or should be desirable to you. Okay, so the first thing I'm going to check is whether this set is consistent. Consistency means there's at least one coherent set that includes them. That is consistency in this language, right? So I will call an assessment consistent if it is included in some coherent set of desirable options. Right? And in that case, if it is consistent, then look at this collection here. It's a set of all this this bold D is just a set of all coherent sets of desirable options. Yeah, so the fat one here is all of them. And I'm looking at all the ones that include the assessment. Because the set is consistent, this set is non-empty. There's at least one in there. That's consistency. Yeah? So this is a collection of sets of desirable options that is non-empty, and therefore their intersection is also coherent. And it's the smallest one, because it's the smallest, it's the infimum of all of them. So this is the smallest set of all of desirable options that includes my assessment, or your assessment, rather. And that is closure. We call this the closure with respect to this family of coherent sets. So closure means the smallest thing that has a property and that includes something else. Now this is what we do in logic, right? In essence, this is just, you give me an assessment, and I'm looking at the smallest, the most conservative, because it contains the least options. The smallest, the most conservative set, coherent set, that is compatible with your assessment. In other words, the set of those options that follow from your assessment. Okay. So, turns out, and this is something that Eric also mentioned, that is actually the POSI, the set of all positive linear combinations of the union of A and this background cone. This is something that Eric explained. Right? So, okay, we have this. It's also called natural extension, this closure, this particular one. Okay. So this is probability theory. It's just not the probability theory that you are familiar with, right? So how can we get to something that you are more familiar with? To do that, we need to go to what we call Archimedean models. And by Archimedean, we mean that something that a preference can be expressed using real numbers. That's what Archimedean essentially means in this context. Right, and there's a number of pioneers there. You see the first generation, the ancient ones, and then the less ancient ones, at least for the ones on the right-hand side. Okay, there's a few people you can recognize also. Right, so what are these Archimedean models about? If you want to learn more about these, this is a paper a few years old where I study this in more detail. So I'm going to tell you a few things. Now, most of the results that I will mention here have not been published. They're part of a book I'm working on. I've decided to give you some advanced knowledge. They're very simple, they're very easy, but I think they're very nice because they work in very abstract spaces. So it's not really very, very difficult, but it's abstract. So, okay. So remember, we had a vector space. Our option space is a vector space. Now, when we want to go to Archimedeanity, when we want to involve the real numbers a bit more, we need a notion of distance. We need to be able to say that two options are close together. So we will use this using a norm. So what is a norm? A norm is just a function here from the options to the real numbers. So this is this norm. This little ball here means put inside an option. So it is crying out for options, this little ball here. And so the idea is if I fill in an option, then what comes out of this machine is a real number. Yeah? And this real number is always non-negative. It is only 0 if what I put in is 0. So this represents, in a way, the distance to the origin. Right? So this means that the distance to the origin is 0 if and only if I am in the origin. Right? And this distance is never negative. This distance satisfies the triangle inequality. Right? So it's a sub-additive thing. The norm of a sum is smaller than the sum of the norms of the options that participate in the sum, and then it's in a way it's a bit homogeneous in the sense that I can take a number out through the absolute value, or okay. So I have a norm. I'm assuming that there is this. So if I have a norm, this means I have a distance, right? And if I have a distance, this means that I can look, if I'm in a point, I can look at all the points that are within a certain distance from that point. I will call that a ball, right? And if I take all the points whose distance to that point is strictly smaller than some number, then I have an open ball. Yeah? And if I have no open balls, then I can introduce a topology, a metric topology. The idea is a set will be open if all the elements in that set, if all the options in the set have a ball around them, some ball around them that is still in the set. That is what I call an open set. And then a closed set will be the complement of an open set. So I have closed sets, I have open sets, I have a topology. I have a notion of convergence. A sequence can then converge using an epsilon delta definition, if you want. Yeah? So this is all basic. Okay, so this means that I have an interior operator and a closure operator, a topological closure operator. What is the topological closure of a set? It is the smallest closed set that includes a set. Another type of closure, in this case topological closure. Yeah? The interior operator is just the dual. It is the largest open set that is included in the set. Right? That's the interior operator. So that's what I have. Now, since I'm looking at Archimedeanity, I also need to look at what I call real functionals. And a real functional is just something that takes an option and maps it to a real number. So it attaches a real number to any option. That's what I call a real functional. And I need a way to express that a functional is bounded. How am I going to do this? Well, I have a norm on my space. I can use this to introduce a norm on the set, on the collection of all functionals. In what way? I'm going to introduce the function norm, or the functional norm, of an operator, gamma, as what? As this expression. So what I'm doing is, in every u that is not 0, I'm taking the value of this operator in u, take its absolute value, and then I will take a relative size. So I divide by the norm of the argument, right? So that I get a relative size. And then I'm going to take the largest possible one, the supremum, over all u's that are not 0. Why do I exclude 0? Because otherwise I would have to divide by 0 here, right? And that thing, if that thing is not infinite, if that is not unbounded, then I will call gamma itself a bounded real functional. That's the notion I need. Now, with all the functionals that I will consider, this boundedness is actually equivalent to being continuous, right? Which means that small changes in the argument will lead to small changes in the value. That is an equivalence. So this is why this boundedness is so interesting, because it actually tells you that if an operator is bounded, typically for the ones that I'll be considering, they're also continuous. There's one more thing I need to make this theory work, and that is a unit. Remember, if we look at gambles, there is such a thing as the unit gamble. That is the gamble that is constant and equal to 1 everywhere. So it gives me, whatever happens in the real world, what I get from this gamble is just one unit. Now, in my option space, I told you these options are real numbers, but what would be a unit option? I don't know. I've given some thought to this, and it's actually fairly general. The only thing that we will need is I can take any option as a unit as long as it is in the positive cone, or rather in the interior of the positive cone. In other words, if I can put an open ball around it and I'm still in the positive cone, then that is fine as a unit. Yeah? So this clearly is a unit, because it's in the unit cone, in the interior, in the background cone. It's in the background cone, and I can put a ball around it. Okay? So that I will use as a unit. So I will take this as a unit element, element in the interior of the background cone. And now everything is ready. Everything is ready for us to do theory. The question is, I have a set, you have a set of desirable options. A D. It's coherent. The question is, can I characterize your D using a functional? Something that maps options to real numbers. That's the question. Well, I'm going to introduce two ways of doing that. They're equivalent. The idea is the following, and you should not be surprised at this point by the following formula. I'm going to introduce two price functionals, an upper price or a buying price functional and a selling price functional. Now, look at it. What does it say? The lambda lower of D in any option U is the supremum of a number of numbers, real numbers, such that, and the such that is interesting. So what happens is that what you see here is what we call a transaction. The positive part of a transaction is what you get. The thing with the negative sign is what you give away. Right? So you get U, and you give away alpha times the unit. So what you have is, and this thing, this transaction is desirable to you. You want it. You strictly prefer it to 0. So in other words, what you're doing is you're getting U and you're giving away alpha times the unit. So alpha is an acceptable or desirable, in this case, desirable buying price for you. You want to buy this U for a price of alpha units. So this is your, which is why I call it a buying price functional. And the other one, the lambda upper, is your selling price functional. It gives you, what you give away is u, so you give away u, and you get beta times the unit in return. So you sell u for beta times u. So this gives you the infimum selling price for u. Okay? And these two functionals are conjugate in the sense that the supremum buying price, the infimum selling price for u is minus the supremum buying price for minus u. You can do a little bit of mathematics and see this relationship immediately. At this point, you ought to be screaming. Screaming with indignation. Because I've written down things like suprema and infima. Are they real? Or are they infinite? I mean, I told you that this was a functional, but I defined a functional as a map from the options to the real numbers. Are these real numbers? You hope so, eh? So do I. So did I when I wrote this down. So did I, yes. But proving it was different, right? It turns out that I wasn't the first one to try and prove this. That happens quite often, by the way. The idea is that this actually, you can prove that, first of all, that these are real. And secondly, you can prove that at the same time, lambda d is smaller than lambda upper of d, hence the notation for all u. You can prove this, provided that your unit is in the interior of the background cone. Otherwise, this thing can become infinite. But if you make that choice, then you're okay. This is always real valued, so that's good. Okay. So now, I have these things. Yeah, this little figure that you see here gives you a graphical representation of what is going on. Right? I have an option u. And what I'm doing is, this is the unit option. So what I'm doing is I'm adding to this option vectors that lie along this, multiples of this vector. So I'm on this line here. Yeah? And so what I'm seeing is that here, I'm still inside D. So all these transactions for all these, they are desirable until I reach the boundary, and there they change sign, right? And so for lambda greater, I'm outside. So this is actually, at this point, there's a distance here that is a negative number in this, a positive number, because I have to subtract here. So alpha will be positive, and then I go in the down direction. So here it will be positive. Here, for a point outside the cone, I have to actually go in the direction of the unit in order to get inside the cone. Right? So here my buying price will be negative. Because I have to go in the positive direction, and there is this minus sign here. This already tells you something. And that is this relationship. My buying price is positive for an option if and only if it is in the interior of D. And it's non-negative if and only if it is in the closure of D. Right? So, this here, with the green line included, is the collection of all the options with a positive buying price, a non-negative buying price. And if I exclude the borders, I get all the options with a positive buying price. So the ones on the border are the ones that have a zero buying price. Right? And this so in some sense, I can use these functionals to characterize D, but only up to the border. Right? So this behavior cannot be represented using this buying price functional, because this buying price functional will not make any difference between, there will be 0 everywhere on the border, so it will not make a difference between this side and this side. So this type of model that we had in desirability, we don't have if we use Archimedean models. We lose it. We lose part of the preference modeling. The boundary behavior is lost. Okay? Good. But what we have up to boundary behavior is this, all right? U is preferred to V, which means that U minus V is desirable if and only if this should have a D here, if and only if the buying price functional is positive, right? Of the difference. So this characterizes, in this way, up to boundary behavior, this characterizes this lambda, this buying price functional characterizes the ordering up to boundary behavior. And this is why we do probability theory, because these things will turn out to be related to probabilities. Let's see how. So it turns out that these buying price functionals and the duals, the conjugate duals, the selling price functionals, turned out to be quite important. So I will give them a name. And the name that I'll give them is, of course, there's many people who came before me, and so I have to honor their choices, which means that I will give it a name that corresponds to what they did in special cases. And I'm talking in this case about Peter Williams and Peter Wally. So I will call any real functional, I will call it a coherent lower prevision if it is a buying price functional for some set of desirable options. In other words, I have a set of coherent lower previsions, the blackboard P lower, and that set is just all the buying price functionals. So I range my D over all the coherent sets, and all the buying price functionals will be in here, and they are the coherent lower previsions. Coherent upper previsions will then be all the selling price functionals, of course. There's no surprise there. Right? So if I range my D over all the coherent sets, and I look at all the corresponding selling price functionals, then I will get the set of all the coherent upper previsions. And then the intersection, things that are at the same time a coherent buying price and a coherent selling price, where these coincide, these functionals, these intersections, we'll call those elements there coherent previsions. So those are the functionals for which that are at the same time for the same set of desirable options, a selling and a buying price function. So this is on an abstract space. You have coherent lower previsions, coherent upper previsions, and coherent previsions. Now, in order to prove that something is a coherent prevision, or an upper prevision, or a lower prevision, what do I have to do? I have to in some way come up with a D and prove that this functional that I have is actually equal to the buying price functional for that D. That's not very convenient. Right? You don't want to work. Now what I want is another way to carry, this is a definition. Now I want an easy characterization. Turns out that they exist. Here they are. Any real functional will be a coherent lower prevision. In other words, there will be some coherent set of desirable options such that it is the buying price functional for that set, if and only if L1 through L5 are satisfied. L1 is probably something that you will recognize. It's the super additivity property. The provision of a sum is greater than the sum of the lower provision of a sum is greater than the lower provisions of the sum of the lower provisions. The second one is the positive homogeneity condition. It tells me that I can take positive constants out of the multiplicative constants out of the lower prevision operator. The third one says that it should be bounded. It should be continuous. Continuity is required for coherence. The fourth one is interesting. It tells me that there's a kind of additivity as well. but it's a restricted kind of additivity. It's called constant additivity. If I add alpha times a unit to any option, I can take the alpha out. That is constant additivity. And the final one is, here is the background ordering. Finally, it had to be here. It says that if U is greater than V in the background, then your buying price, supremum buying price for U should be higher, at least as high as your supremum buying price for V. So those are the properties for coherent lower provisions. For coherent upper provisions, you have the dual ones. I'm not going to write them down. But it's interesting to look at the properties for coherent provisions. Coherent provisions are additive. They are bounded. They are normed. The provision of the unit is equal to 1. And they are positive in the sense that all the positive options in the background should get non-negative precision. All right. I didn't include the linearity condition, so I didn't multiply with lambda and mu here and get a lambda and mu here, or in other words, I didn't include the homogeneity conditions. Why not? Because they follow. They follow from this one and the continuity condition, right? So they will follow immediately from this. So when you see this for a provision, you can replace this always by a linearity. So the provision of a linear combination is the linear combination of the provisions, right? But it follows from these two, and I want it to be as sparse as possible, right? So this, on any space, on any vector space, this is what we call a coherent provision. De Finetti would have liked this, because that's what he actually did, right? Not for him, there was something more, but this generalizes his idea of what a provision is. Okay. Now, this is all very well. Yes, Erik? Yeah. That is because you took as a unit something that was so trivial that that it follows. Well, it follows. It doesn't follow from the rest, but you will. Well, I'll explain later. You will see immediately what is going on. Just a little bit of patience. I was almost there, right? Okay. We know that the background cone is also coherent, right? Why? Because it's a convex cone and it includes the background cone, right? So it's coherent. That is what we want. And it doesn't include 0. So it's coherent. It's actually the smallest of all coherent cones. It's the smallest coherent set. But since the background cone is coherent, I can associate a price functional with it. The buying price is a selling price. So this is what I'm doing here. I'm associating a lower buying price with the background cone. And since it is coherent, this will be fine. This will be a coherent lower provision. It will be the smallest coherent lower provision because the background cone is the smallest coherent cone. And I can define a selling price functional, and that will be the largest coherent one. And I will give these a name. I will call this the infimum operator that is associated with this vector space and this background ordering, and the supremum operator. So the infimum of U is just the buying price functional that is associated with the background cone evaluated in U. In other words, it's a supremum alpha such that U is still greater than alpha times the unit. Okay, so this introduces two new functionals, the infimum and the supremum operator. They are coherent lower provisions and upper provisions. The characterization now simplifies. Instead of 5, I have only 3. L1 and L2 remain the same. I have a superadditive and positively homogeneous functional, but the three remaining ones under these two are replaced by the functional dominates the infimum everywhere. It is larger than the smallest one. And the same for upper provisions and the supremum. And this one, this is even cooler. The provisions are additive and they dominate the infimum. Two requirements for the provisions. So coherent provision is something that is additive and dominates the infimum. On this abstract space. And I'm going to say something important. What determines whether something is a provision? The additivity, first of all. Yeah, right. And therefore the linearity. Together with this, I get with this and this together gives me linearity. Yeah, but the additivity, yeah, that determines what. But something else, right? Something else determines whether something is a provision, namely the background. Whether an additive functional is a provision, is a coherent provision, is completely determined by the background on the space and on the norm, indirectly. The background tells me whether something that is additive is a provision. Nothing else. Yeah. It's important for later. So if I choose another background, I will have other coherent provisions on the same space. And then we come to the question that was there before. What are reasonable backgrounds, right? We'll come back to that. Okay, one more result that you need, something that's also been mentioned, is the lower envelope theorem. So any real functional from the options to the real numbers will be a coherent lower provision if and only if it is a lower envelope of some set of coherent provisions. Right, so here we come to Creedle sets. M is a set of probabilities, mass functions in the lecture of Monday, in Monday's lecture. Now this has been abstracted away. I have a set of linear functionals now, a set of coherent provisions, and I take the lower envelope in this way. I just take the value of P in the option U that I'm looking at, and then I range the P over all the elements of M. That gives me a collection of real numbers, and I take the smallest one, the infimum one, every time, and that gives me a functional, and that is always a coherent lower provision. And the largest, for a given coherent lower provision, the largest M that does this is this one. So the set of all the P's that dominate the lower provision. All right? And this is a convex set, clearly. It's a convex set. Any convex combination of P's will also do it. And it is closed in the topology that I just generated using the operator norm. And also in the weak topology, but that is a technical detail. So it is weak closed. And therefore also weak compact, but that is mathematical detail. So this is actually a very special case, one of these special cases of the Hahn-Banach theorem has like an infinity of special cases, and this is one of them. Okay. In particular, of course, the smallest lower provision is just the lower envelope of all the coherent provisions, right? So if I know nothing, if I don't know what my probability or my provision is, then I take all of them, and that gives me the infimum operator on that space. All right. Just as a curiosity, once I have the infimum operator, I can introduce two orderings that you will probably recognize. The first one is I say that an option is dot preferred to 0 if its infimum is strictly positive. And it is, so this is strongly dominant I will call this. So the ordering that is induced by this is what I call the strong dominance ordering. In game theory, this is a thing on real valued spaces, right? The weak dominance ordering is this one. Something is preferred to 0 if its infimum is greater than 0, but it's not 0 itself. That is the weak dominance ordering in game theory. Right, so I introduced them in this context as well. Now, there are 2 homework exercises. If you're interested in this, this is a good way of getting into the material. Show that this ordering is stronger than the background and that the background is stronger than the weak one. So if something is strongly preferred to 0, it is preferred to 0 in the background, and then it is also weakly preferred to 0. Moreover, and this is even cooler, the infimum operator, if I take this as a background ordering, or I take this as a background ordering, or I take this as a background ordering, the infimum operator is always the same, which means that choosing between any of these will not affect my notion of coherence for lower and upper previsions. It will change my notion of desirability. There's another way in which desirability is a stronger and a more potent notion than coherent lower previsions, because I can play around, I can fool around with the background in this way, and it does not change my notion of coherence. Why doesn't it change my notion of coherence? Because the infimum operators determine what coherent is, besides the additivity property or the superlinearity property. Okay? All right. We're done with the red part. Congratulations. Are you still awake? More or less. I have about a few minutes to go. Let me check if I can already... yes. Sorry, yes, Creedle set. Yeah.
So in your case, is no unique Creedle set?
Is no unique Creedle set, but there is a unique convex closed one. Yeah, so there is a one-to-one correspondence between convex and closed sets of provisions and lower provisions, coherent lower provisions. Yeah? But, of course, I can take... If this is not convex and closed, then I will still get a lower provision, but there will be many that do it. The extreme points will do it. The extreme points of this one will do it. Yeah, also, that is another thing that you saw on the first day, that you can work with the extreme points as well. Right? Okay, classical probability now. So this is probability not as you know it, although I try to come closer using these functionals. Now I'm going to show you, or you are going to do it yourself later on. Right? I'm going to show you that you recover classical probability as a special case of this. So classical probability, you just choose, what do we have to do? We have to find an option space that corresponds to classical probability. We have to choose a norm and a unit. 3 things, and a background. Right? So let's begin with, what is the option space? Well, you already know what the option space is. The idea is that options now in classical probability are gambles. So you have some X, a collection of elements, a possibility space, and you have a random variable, a variable that assumes a value in there, but you don't know what that value is. Okay? Now what I can do is I can attach to each of these elements, x1 through xn. I'm going to look at the finite dimensional case only to make things simple. Right? I could do more dimensions, but let's make it as easy as possible. So what I'm going to do is I'm going to attach to each of these possible values of the random variable, I'm going to attach a number, a real number. And that real number is the reward that you get if actually the outcome is that number. So if the outcome x, the thing that I don't know, is xn minus 3, then your reward will be that number that I attach to x minus 3. So what I'm doing essentially is I'm taking maps from the possibility space, the set of possible outcomes, to the real numbers. And these are uncertain rewards. Why are they uncertain? Because if I don't know the argument, typically I won't know the value of the function. So I'm uncertain about the value of the function, and the value of the function is your reward. So I have an uncertain reward. Right? And I told you options are uncertain rewards. So in this case, I have an uncertain reward, and I'll call it a gamble in this case. So I have gambles, two-dimensional case. Any point in this two-dimensional case, so in this case my possibility space is AB. I have a gamble, its value in A is here, its value in B is here. The gamble is completely determined by the value in A and the value in B. It's a point in this two-dimensional space. It will give me a negative reward if B occurs and a positive reward if A occurs. Right? Okay. So I know what the options are. They constitute a linear space. That's fine. I need a norm. What norm am I going to choose? Does it matter? No, because I'm in a finite dimensional space, all norms are equivalent. Whatever norm I take, the topology that is generated by it will always be the same. It will be the metric topology. So I'm going to take this one, right? It's the one that is easiest to express. Or I could take the Euclidean norm, would be fine, right? But typically you take the supremum norm, because that one also works on infinite spaces, and then you have to work with bounded functions. So I take the supremum norm here. So the supremum, I will write this as the supremum of the absolute value of f, and that is the norm of f. So I'll take that. And then the unit, well, the unit will just, I told you, the unit that I took in the general space was an abstract version of this unit, thing that is always 1, whatever the outcome, whatever the value. So this one here, that is the unit that I'm going to take. So I have a unit, I have a norm. I'm there. The only thing now, so I have sets of desirable gambles. I have the whole thing, the whole theory. I'm not going to repeat that. But let's look at what the provisions are. There's one thing that I don't have, that I forgot. But since it's now 3 o'clock, this is the ideal moment to stop and take a break, right? So let's take a break, and after the break, and after the commercials, you can come back. So we're still in the classical case of classical probability. At least we found the linear space, we've taken a unit, and we've taken a norm. The one thing that is missing is the background ordering. I'm going to claim that we can derive this background ordering in a sense, in some sense, by reasonable arguments, and in some other sense, by physical arguments. Okay, and this is what I'm going to try now, so bear with me. I'll try to go as slowly as possible, because later on, I want you, in the next hour, I want you to do the same thing for quantum mechanics. Right? Same ideas. So pay attention. So, background ordering. Again, what is this background ordering? It's the ordering that is always there, even if you have no preferences at all. It should still be there. It represents your, or at least it represents everybody's complete ignorance. So what is this set of desirable gambles under complete ignorance? What is this smallest reasonable cone of desirable gambles? I'll call it D, because that is easier to write than U greater than or equal to 0. So let me call it D. Now for this argument to work, this is the place where I need to explain to you what I mean by indifference. Sorry, not by indifference, but by the desirability. Because desirability means to strictly prefer. But what the hell does that mean? Strictly prefer. Yeah, 0 is not in there, you know? And I can give you a number of axioms, but what does that mean in terms of things that you and I could do? We could sit together and I could tell you, is this do you strictly prefer this to 0? And I probably would ask me, what does that mean, strictly prefer to 0? I'm going to give an interpretation in terms of behavior, what we call a behavioral interpretation, right? Something that can also be operationalized, in a sense. I'm going to introduce 2 sets of gambles. The first set of gambles is the gambles that you accept. Now, accepting is not the same as finding desirable. Accept is, I offered them to you, and you say, yes, I want it. And that is easy, that is operationalizable. I ask you, do you want it? And you say yes. And that is when we say that the gamble is acceptable. You want it? Okay, fine. I'm going to introduce another one, R. And those are the gambles that you reject. I offer them to you and you say no. No, sorry, I don't want this. That is clear in terms of meaning, right? I hope so. If anybody thinks that this is not clear in terms of meaning, please tell me, because then we have a strong difference of opinion. Okay? But at least we can write this down. Okay? Then there are 2 more things that I can derive from this, namely your desirable options. What do I call desirable? Desirable is something that you want, so it's definitely acceptable. But you don't want to give it away. You want to keep it, which means that you reject the additive inverse. So you accept it, and you reject the additive inverse. So it's the intersection of the gambles that you accept and for which the additive inverse belongs to the rejected gambles. So desirable means I accept it and I really don't want to give it away. When are you indifferent to a gamble? So what is your set of indifferent gambles? Indifferent are the ones that you accept, that you want, and that you also want to give away. So those are the ones like this. Those are your indifferent gambles. So what I'm going to do is I'm going to develop an argument in terms of this. Why? Because this is something that is operationalizable. I can explain this to you. Whereas it's more difficult to explain it in terms of desirability and indifference. But, so you see, I'm going to develop an argument, and then I'm going to look at a very special case, the case where your acceptable, this is a special case, where your set of accepted gambles is then equal, so that is general, and then I'm going to look at a special case where the gambles that you accept is the union of your desirable ones and the ones you're indifferent with. This is a special case, and this is the case that eventually corresponds to the whole notion of desirability that we've been developing here, right? The arguments are developed in a paper that Erik and I and Philip Hermans wrote a long time ago, and that Alessandro was talking a lot about on the second day, right? But if you want to know more about this, that is the place to go to. I'm just going to tell you that, okay, try to explain the basics, and then we're going to look in this framework here. That is the framework that I developed the preceding theory in. So this is a bit of background on that. So now I'm going to try and develop this argument. Okay. Okay, so let's see, acceptable gambles. My claim is that if I have a constant, a real number that is positive or non-negative, then if I multiply that number with the unit gamble, then I get a constant gamble that is everywhere mu. So whatever happens, this is mu. And this is non-negative. I claim that it's reasonable to accept it. So yeah, this is the accepting non-negative gambles. I mean, any reasonable person should accept something that is non-negative. That's my claim. You can disagree, but then again, we will have a disagreement. Okay, so this whole argument is based on this idea, right? Second step. Okay, suppose that I have a gamble f, not constant, but its minimal value is greater than mu, and mu is greater than or equal to 0. So I have a gamble, and its reward is always greater, or at least as large, as this constant positive gamble. Since you accept this constant positive gamble, and since you cannot get a reward that is smaller than this by accepting this, you should also accept this. Right? From this, it follows that the set of all gambles F, for which the infimum is greater than 0, is, or should be, a subset of the set of all acceptable gambles. First argument. Second argument. If mu is strictly positive, strictly negative, excuse me, and I look at the gamble that is constant, unit. That should be unit, I'm sorry, right? And I look at the gamble that is constantly, everywhere this negative number. If you accept this gamble, you accept a sure loss. You accept to pay, whatever happens, to pay the amount mu. I claim that this is not rational. Right? So you should reject this. Second step, if I have any gamble and its supremum is smaller than mu and mu is smaller than 0, then I have a gamble and its maximal reward is not larger than this minus mu. So from this gamble, I cannot get something that is better than this negative gamble that gives me negative everywhere. I should reject it. Sorry, F should be rejected. Which tells me that, because of this, all gambles F in G for which the supremum is strictly smaller than 0 should be rejected. Okay. This is the argument here. This is the argument I gave. So, in the case of 2, well, it says that you should, your set of acceptable gambles should always include this green thing. And your set of rejected gambles should include the red thing or the orange thing, whatever you want, but not the boundaries. So the supremum strictly greater than 0. That is that. So what I now have is lower bounds on the set of rejected and the set of accepted gambles. I also need an upper bound. This is trivial in some sense. I need a useful upper bound. And this is where the idea of complete ignorance comes from. This is not typical of complete ignorance. This is typical of rational behavior. But where does the idea of complete ignorance come from? That will put an upper bound on the accepted gambles. And then I will start to argue. Okay, an upper bound on the accepted gambles. I claim this is a statement that to me represents complete ignorance. If you are completely ignorant, and A is your set of acceptable gambles, then if you accept the gamble F, and there is another gamble G, And the possible values, so f of capital X is the set of all the values, right? So f of x is just f of x for x in x, right? It is the range of the gamble. It is the range of the gamble. So all the values that if you engage in the transaction, all the possible rewards that you could get. So f of x is something that you accept, and f of x is just the set of all the rewards that you could get, possibly can get, if you engage in the transaction. And now I'm looking at another gamble, G, and the idea is that for that gamble, all the things that I could get is a subset, is included in all the gambles that I could for the other gamble. Then, complete ignorance, if I'm completely ignorant, I should accept that, G also. Think about it. If you know something, if you have definite beliefs, if you have a probability, for instance, this will not work. You can provide a counterexample. Very easy. Right? But if you have no beliefs at all, this is actually what I claim. To me, this represents complete ignorance. That is, in terms of behavior, I'm going to give you another argument why this represents complete ignorance, and that is a symmetry argument. M, right? M. Okay. I have my possibility space, X, so all the possible values, and I'm going to introduce a transformation of that possibility space. So a map from X to X. It could be a permutation, or it could be a surjection, right? Whatever. But it's a function. A transformation of, it's a mapping. Defined everywhere. So what I'm doing is, I'm transforming my possibility space, and now I'm going to define T sub T as the map, the corresponding map on gambles that turns any gamble into F after T. So this is what I call the transformed gamble. So the idea is, so in other words, T of F in X is just F in T of X. So I'm transforming my possibility space. Well, my claim is, and this is an exercise, and it's a homework exercise, we're not going to do it here. My claim is that the previous statement that I had is equivalent to my set A is invariant under all these transformations. So these are the gambles that don't change if I do whatever I can do with my possibility space. And again, typically this symmetry argument is what is used to defend ignorance. Right? If whatever I do to my possibility space does not affect whether I accept the gamble or not. And this is equivalent. So in other words, if a gamble is in A, then TT of that gamble is also in A, and this for all transformations T. That is that argument. And it's completely equivalent to it. You can prove this. So there's both a symmetry argument and an argument in terms of behavior. Well, okay, so let's do this argument here. And now I'll do it here. Prove that this gives me an upper bound on A. First of all, take any gamble that you accept. Any gamble in A. Because, and now consider the gamble, take any X in my space. And consider the constant gamble whose value is f of x. So this is a constant gamble. Everywhere the value is f of x. Since, yeah, it's difficult to point. Since this gamble, call this gamble g, the range of this gamble is just f of x, the singleton f of x. Is a subset of x greater of x. So the range of this gamble is, so the range of, if I take all the possible values of this gamble, that is the singleton f of x, small x, which is a subset of f of x. Right? So by this thing, I must accept it. And I must accept this kind of gamble for all x in x. Now, if I accept it, there is one more thing that I need to tell you here that I haven't told you before, and that is there is a rationality axiom related to this, and that rationality axiom tells me that the intersection of A and R should be empty. This is what we call the no confusion requirement. You can't at the same time accept and reject a gamble. Right? Either you say yes or you say no. Or you say nothing. That's also possible, right? If I draw this, it could be that you're outside this and then you say nothing. Here you say yes, here you say no. Okay. So this means, right, if it's in here, if it's in A, it can't be in R. So I know it's not in R. Right? It's not in R. But since R, in R, inside R, are all the constant negative gambles. So if it's not in R, this constant gamble here can't be negative. So it must be non-negative. Because if it were negative, it wouldn't be in it would be in R. Right? So it must be positive. Or at least non-negative. Since this is a constant gamble, right? So this means that this gamble can't be in R, is not in R, and therefore this value should be non-negative. Because if it were negative, it would be in R. Okay, so what I have is that this function is everywhere non-negative, so its infimum is greater than 0. So what I found is that on the one hand, on the previous slide, I found that the infimum, if the infimum is greater than 0, then it should be an A, lower bound, and now I have the upper bound. If it's in A, then its infimum must be greater than 0. So in other words, you can't get any tighter than this. A is equal to the set of gambles that I accept by this argument are precisely the ones that have infimum greater than or equal to 0. What does this imply for my set of rejected gambles? Well, I already know that if the supremum is negative, then it can't be in the rejected gamble. But this one now gives me also this inequality. Why? Look at this picture. If the infimum is greater than or equal to 0, it's in A. It's here. So it can't be in R. And vice versa. If it's in R, if it's in R, it can't be in A. So the infimum must be smaller than 0. So I have an upper and a lower bound for R. Yeah? There's no rational. Is there a rationality axiom here? Here. this that it should be 0, empty, right?
But why? Because this, like from behavior perspective, this implies that I am indifferent between two choices.
No, it tells you, no, that doesn't say that. It says that you, any gamble in here, you tell me, yes, I accept it, and yes, I reject, I don't want it. That's not being indifferent. That is being confused. I didn't mean that in any personal, but it's just describing this type of behavior, right? Yeah. If you told me that, I said, okay, which is it? Right? I mean, come on, be serious. How can you say yes and no to the same question? Right, it's a typical consistency requirement in your model. Yeah. Okay, so now I have A and R, I have bounds on it. I will now, because what I need is minus R and minus A. So let me write them down. Minus A is just minus the gambles that are in A. So the infimum of minus F must be greater than 0, which means that the supremum must be smaller than 0, because the infimum of minus F is minus the supremum of F, right? And similarly, the supremum of minus F is minus the infimum of F. Okay, so minus R, same thing, supremum of minus F smaller than 0 means infimum of F greater than 0, and this one here, okay? And now I have what I need. What I now do is I take the intersection of A and minus R, and I look at what's in the intersection of A and this one. So the infimum here, the infimum of it must be greater than 0, and it must be strictly greater than 0. So what I get is, for D, which is the intersection of A and minus R, the infimum must be greater than 0 on the left-hand side. And on the right-hand side, I get the infimum must be smaller than 0, and the supremum must be larger than 0. Oh, no, sorry, the infimum must be non-negative, and the supremum must be positive, which means that the infimum must be non-negative and the gamble can't be 0. Right? That's the only remaining possibility. So I find these two bounds for, I don't know if you recognize them from before, these inequalities. This gives me the strong dominance. When I write it in terms of gambles, this gives me the weak dominance ordering that I find as bounds. And for the intersection of A and minus A, that's easy. The infimum must be non-negative, and the supremum must be non-positive. There's only one gamble that does it, that is the 0 gamble. So the only indifferent gamble when you know nothing is the 0 gamble. And these are the possible values for the desirable gambles. This is very general. Now I'm going to restrict myself to the framework where the gambles are accept are the union of the desirable gambles and the indifferent gambles. Let me draw this again. So these are the two possibilities in this case. Either it's not included, the infimum 0, or the infimum 0 is included, but 0 is not in there. Those are the two possibilities. You're going to tell me there could be a mixture of the two, and then I'm going to tell you no, because of the symmetry argument. If I take any permutation, remember, my A must also be permutation invariant, so it must be symmetry there as well. Okay, so these are the two possibilities. Okay. But now I'm going to look at the case where the set of acceptable gambles, which is the ones where everything is included, and the indifferent gambles It must be the indifferent gambles and either of these two. This is the only one. Because if I add 0 to this one, I'm not getting all the accepted gambles. So this is the only remaining one. The weak Pareto ordering is the only ordering that represents complete ignorance according to this simple argument. Okay, this is why I'm using this one all the time in gambles. Right? This is why Eric also gave you that drawing, because I asked him to. Right? Okay. Okay. Small first exercise. I'll give you like 5 minutes to solve this. Remember we had, I'm not sure if you have your laptop with you, otherwise I'll give you the formula on the blackboard. Let me write it here and then I'll clean the blackboard. And so the infimum operator that is associated with a background ordering given in an option U is the supremum alpha such that U is still greater than the unit of U times alpha. This is the general formula for the infimum operator. So my question is, in this context, where I have a background ordering that is the ordering that you just saw, the weak dominance ordering. So you know this ordering. You know what the unit is, that is the constant gamble. What is the infimum operator? In other words, what is the infimum inf greater than of a gamble f? That is the question that I'd like you to answer. I'm going to clean the blackboard and you have 5 minutes to think about this. So who has the answer? Who has found the answer? Who has tried? You have the answer. Yeah. Yeah. So those who have the answer know why I called this abstract infimum operator an infimum operator. Because the infimum of a gamble in this abstract thing is actually equal to the infimum of the gamble as we saw it before. Let me prove it to you. It's here. So this infimum of f is supreme of alpha such that f minus is greater than 0, where this is just, in essence, pointwise inequality, right? That is the idea. So it's a supreme of alpha for which the infimum is greater than 0 and f is not equal to that. So because then otherwise the infimum would be 0. And this infimum, the alpha, since this is a constant, you can take it out. So the infimum of f should be greater than alpha. And f should not be equal to constant alpha. Right? So if f is equal to the constant alpha, and this drops away. Then this drops away. But then, of course, if f is equal to the constant alpha, then I get that this is the infimum anyway. And if f is not equal to some constant gamble, then this drops away. And then I have this, and then the largest alpha for which this holds is actually the infimum of f. So this infimum operator taken in the option f is equal to the infimum of the gamble f. They coincide. Now we will remember that I used this to define a weak dominance ordering on this abstract space. That coincides with the weak dominance ordering that people use in game theory and in decision making. Yeah, it's the same ordering. And the strong dominance ordering also, for that matter. Right, so that's one thing. But now the real stuff, right? So now I have a background ordering, I have a unit, I have a norm. I can do desirability theory. I can do sets of desirable gambles. This is what Eric told you about. We can look at the Archimedean models, and there I have coherent lower provisions and coherent provisions. And coherent lower provisions are just lower envelopes of coherent provisions. So if I look at coherent provisions, should be enough. The question now is, what are the coherent provisions in this theory, in this special case? What do they look like? Remember, they are the linear ones, but they must also dominate the infimum operator. That's where the background comes in. Right? The background, remember the background determines what a coherent provision is. So you have two things to use. You can use the linearity and you can use the background. So the next exercise is, what are the coherent provisions? Characterize them for me. And I will give you a hint. That is that in this, so in general, I have a linear space, right, of gambles. And there are two special directions in this linear space. The gambles that are here, whose A value is 0, and the gambles that are here, the gambles whose B value is 0. Right? So this gamble here is represented by this. And this gamble here is represented by this. So this space has two privileged directions. And in general, this gamble space has privileged directions. Remember this for later. These directions, I can't do whatever I want with them. Right? If I rotate this, I will not get a frame of reference that is physically meaningful. The only thing I can do is permute. I can't rotate over angles that are smaller than 90 degrees or 100, not multiples of pi over 2. Right? Because these axes have physical meaning, in a way. Okay. Now, this is a unit vector. This is what we call in linear algebra, this is the standard basis, right? This is the standard basis. So the unit vector in the A direction, I can also write that as the indicator of the set A, of the singleton A. Because it is 0 on A in the A direction, 1 on A and 0 everywhere else. And this one, EB, I can write that as an indicator of B. And in the general case, I have a unit basis E1 through En, right? Which is just, and so this means that any gamble, any vector can be written as a linear combination in this unit basis. And if I write this down, this becomes the sum over all possible values of x, f of x, times the unit vector in that direction, so indicator of the set x. This is a decomposition of any vector f, any function, in terms of the unit basis. I can always do this. Okay. Now use linearity. The rest is up to you. You get 5 minutes. And once you've done linearity, there's one more thing to do, that is the background. You need to use that. If a gamble is greater than 0, then its provision must be greater than 0. So what are, given this background and given the linearity, what are in this theory the coherent provisions? What do they look like? Yeah, but give some time to the others to Okay, very quickly. P of f is equal to P of the sum over all x in x of f of x times the indicator of x. I'm going to use linearity. These are the coefficients, these are the functions, these are the gambles that I'm using, so I'm going to take linearity, so I can take the sum out, I can take the constants out, and I get the probability of the indicator of x. And I will call this P of x. So this can, in principle, be any real number. So these are all the linear previsions. In order to see what these guys are, I need the background. The background will tell me what the reasonable provision is. So the second thing that I will use is that P of f is greater than the infimum of f. And if I go to minus f here, then P of minus f, which is minus P of f, because of the linearity, is going to be greater than minus the supremum of f, so this will become. So P of f is squeezed between the infimum and the supremum. Okay, first thing, plug in special values of f. P of x is the indicator, is the prevision of the indicator of x. So let's see what happens if we plug in for f the indicator. What is the infimum of this function? 0, right? So this should be greater than 0. And what is the supremum of this function? 1. All right. I already know that this little p is between 0 and 1. But I know something more, namely that P of the unit gamble, which is the gamble that is constant everywhere, is greater than the infimum of the constant, which is 1, right? And smaller than the supremum, which is 1. So the P of the unit gamble is 1. But the unit gamble is also the sum of the indicators. Yeah, if I sum all the indicators, then I get 1 everywhere. So P of the unit is the sum over all x of P of x. So P must be a mass function, a probability mass function. This is what the background tells me. The background tells me that I can't just use any linear function. I must use one that is actually an expectation operator that corresponds to a probability mass function. Okay, let's go and have a break for a quarter of an hour. No? Or is it? No, I have more time. Right. Or do I? Oh, wonderful. How great. Oh, lovely. I love you. I was getting worried. Okay, so what have we done? In summary, we have applied our general theory to a special case, and we've argued using some physics, I think, or some general acceptability arguments, what the background cone should be. And this has given us probability theory. Now the big step is, can we do the same for quantum probability? We have this general framework. If we use physical arguments to determine what the background is, will we recover quantum probability? The answer is yes, of course. I wouldn't be here if it weren't. But still, I mean, let's discover this. Hopefully we will find that this is indeed the case. And then the conclusion, of course, will be obvious, right? That quantum probability is not all that different from classical probability. It's just the same, two faces of the same thing. And I think that will be the takeaway message. But we're not there yet, right? We haven't proved it yet. We need some quantum theory now. This is where we come to the right side of the presentation. Quantum probability. And as I am wont to, I'm going to give you a few of the pioneers. The top ones are the real pioneers. And on the bottom, there are a few people who have also dabbled in this. So Alessandro, who you've already seen, Alessio Benavoli, and Marco Zafalon, are the people who started this nonsense. Right. Okay, so now this is the part that gets really boring because I need to review the basics of, this is what I'm afraid of, right? The rest is, I can make it easy, but this is the tough part for you, right? I need to take you through the mathematical basics for quantum theory, right? So let me begin. I'll work in finite dimensions. I know that physical systems typically have infinite dimensions unless you isolate them well. But let's just make things easy. Finite dimensional quantum system. A qubit, for instance, the thing that is used in quantum information theory to build quantum computers is just a very simple finite dimensional quantum system. An electron with 2 possible spins, for instance. And nothing else. You disregard everything in the background. I mean in the physical background. Mustn't confuse backgrounds here. Okay, so the idea is that what is typically called the state of such a quantum system, the thing that describes it mathematically to a certain extent, or completely, depending on the interpretation that you give to this quantum theory, is something that lives in a Hilbert space, a complex Hilbert space. So it's a linear space. So in this case, X is not a set. In this case, X is a linear space. A linear space over the complex numbers. So the constants, the scalars, are complex numbers. So I'm going to add vectors, finite dimensional vectors. I'm going to add them together, and I also allow myself to multiply them by complex numbers. So this is why I call it a complex Hilbert space. And so any element of that complex Hilbert space will be called a state, a pure state, and in the language of Dirac, a ket. Yeah, so, and we will denote it, I will use the Dirac notation, I will denote it in this way. So it's a bit of a funny notation, but it makes sense once you think of it. I'll try to show why it makes sense. Okay? So Hilbert space is complex, that's fine. It's a complex linear space, or linear space over the complex numbers. It has one other important property, and that is that it has an inner product. So it's provided with an inner product. And an inner product is just a map that takes states to complex numbers. So what you do is you take 2 states. It's a little machine that takes 2 states and uses the 2 states to produce a complex number. That is an inner product. And it has a number of properties. If I plug in the same argument, so if I take the inner product of something with itself, the result must be non-negative. It's only 0, so it's non-negative. It's only 0 if the ket that I plug in is also 0. Interestingly, it's kind of commutative, but then again not, in the sense that if I switch the arguments, then I get the same result, but complex conjugate. So this bar means complex conjugate. And then finally, if I look at, if I plug any vector in here, any ket in here, this little ball means plug me in. Right? If I plug anything in here, so what this means is look at the second argument. This thing is linear in the second argument. If I plug in a linear combination in the second argument, then the result will be a linear combination of the images. So it's linear in the second argument. It will therefore also be kind of linear in the first argument, provided that the constants that I take out, I have to take the complex conjugate, right? So it's kind of linear in the first argument too. All right? Now, what does that mean? This means that if I take a constant phi, so if I take a non-zero, or whatever, if I take a ket here, psi, sorry, then, and I use this to construct a function from the states to the complex numbers as follows. So any ket psi, phi will be mapped to the inner product of psi and phi, right? So this is kept fixed, and I'm looking at the behavior where I change the phi. And this is a linear functional. It takes vectors to complex numbers, and it is linear. It's a linear functional. Right? This linear functional, we call that a bra. Yeah? And we denote it not by the ket notation, which has the little thing pointing forward, and the bar before it, the bra, has an arrow pointing backward, and a bar behind it. This is what we call a bra. So this functional is called a bra, or a bra vector. Okay? And then we can see the inner product as the action of this bra, acting on this ket to form a bracket, right? That's where the terminology comes from. So this bracket is a combination of this bra working on this ket, and it's the inner product of this ket with this ket. Right? That is where the bracket notation comes from. Right? So that's inner products. Are you still with me for this? Good. Two things with the inner product. This inner product allows me to say what a normal or normalized ket is. And if I have two, so if the inner product of a ket with itself is 1, I will call the ket normalized. If the inner product of two kets is 0, these two kets will be called orthogonal. So I can have a notion of orthogonality in this Hilbert space. Okay? Right. Well, so now we have the vectors. The next thing we need to do quantum mechanics, besides the vectors, is linear transformations of these vectors. So linear maps from vectors to vectors. A map that takes a vector to another vector. And I will call that a linear operator. So operators will have hats on them to identify them. It's a pain in the rear end to write everything down with bras and cats, with all these extra symbols that are totally unnecessary, but it helps sometimes, all right? So a linear operator is just a map that goes from states to states, in a sense, from X to X, from the Hilbert space to the Hilbert space. It takes a ket and it turns it into another ket. And it is linear, so it takes any linear combination and it maps it to the linear combination of the images of the contributing kets. So it's a linear transformation of state space. Now the interesting thing is that if I have an inner product, I can use this inner product to define a new operator associated with it, and that is the adjoint operator. And the adjoint operator, what happens is the following. I'm going to look at the right-hand side. So what I'm doing is I'm letting A work on the second argument. Right? And then I ask myself, is there another operator that works on the first argument that has the same effect? Turns out there is always one unique operator that does this. I'm not going to prove it, but... And this operator that has the same effect as the first operator that works on the second argument, but now working on the first argument, this operator is called the adjoint operator. And we denote it by A cross or A dagger. Yeah. There's a small argument to show that the adjoint of the adjoint is the original operator. I'm not going to do it here. We don't have enough time. But that is a small exercise, yeah? To show that the adjoint of the adjoint is actually equal to the original operator. So taking the adjoint is what we call an involutive operation. Right? Okay, 1:15. time to let it sink in. And we're going to go on for another hour of this misery in a quarter of an hour from now. So yeah, and please come back in the same way of organizing yourselves, because we'll do a few more exercises later on. Yeah. Okay. Let's get started. Let's get it over with. Let's put an end to all this suffering. So we had adjoint operators, right? We know how to define an adjoint. You will remember the adjoint is what happens if I move my operator from here to here. It has no effect. And I turn it into the adjoint. That is the idea of an adjoint operator. Okay. When is an operator self-adjoint? Well, clearly if it's equal to its adjoint, right? Then I will call it self-adjoint or Hermitian, after the great French mathematician Hermite, who first thought of this. Okay, so but interestingly, so what does it mean? It means that if I have an operator A here, moving it to the other side of the inner product, I would have to write the adjoint, but the adjoint is equal to A. So I can just go switch my A from the right side to the left side, and vice versa, without any effect. That is the idea of self-adjoint. Now, because it doesn't matter where I put the A, I will just put it in the middle. Doesn't really matter. And so I introduce this new notation in the bracket notation. This is, for a self-adjoint operator, this is what is the same thing as the two things above, right? I can use this, and this is cool. I can now use this. Now here, the phi and the psi and the phi, sorry, can still be different. What happens if I take psi equal to phi? Yeah, so then I have phi a phi. Okay, so I know that this is equal to this. So it's equal to the inner product of phi and a phi. I'm going to move the a to the other side, and since the operator is self-adjoint, that doesn't matter. I can write that, right? But now I want to go back to the original situation. I can do that by changing the arguments. But remember, in an inner product, if I change the arguments, I have to take the complex conjugate. So what I have is that this thing is equal to its complex conjugate. So in other words, this thing is real. It's a real number. Yeah, so this is called the quadratic form associated with the operator A. For a self-adjoint operator, this quadratic form is a real number. Right. Okay. In quantum mechanics, these Hermitian operators represent measurements. My system is in a certain state, in a ket, and I will perform a measurement on that system, and a measurement corresponds to a Hermitian operator, right? And its eigenvalues, I'll come to that later, will be the outcomes, the possible outcomes of this measurement, and they are typically finite in number. So any measurement in this finite dimensional system has only a finite number of possible outcomes, and that is why this is called quantum mechanics, right? Because every measurement that I have only has a finite number, in this case, finite dimensions, finite number of possible outcomes, right? And this is why we use Hermitian operators. Why? Because we will see that their eigenvalues are real. Measurements can only be real numbers. If we measure something, it can only be a real number. So that is, and because they have finite number of eigenvalues, so that is why we use Hermitian operators for measurements, in a sense, one of the reasons, but okay. So later on, I will tell you that these measurements are our options. These will be the gambles, if you want, these measurements. They will live in a space. Now, in order to be options, possible options, they must live in a real vector space, not a complex one. Remember, X is a complex vector space. These measurements must live in a real vector space. That is, if I multiply them only with real numbers, everything is okay. I can add them. They themselves can have complex things inside them, but I'm only going to multiply them with real numbers. I'm going to work over the field of the real numbers, and they will constitute a linear space. Okay, so if they constitute a linear space, I can represent them as matrices, right? If I choose a basis in my space, and I can represent every operator as a matrix. Yes? The outcome of a measurement? So I associate a measurement, I will repeat this later, I associate a measurement with such an operator A that is self-adjoint. And it's the eigenvalues, I will later explain what eigenvalues are in more detail, but these are the possible outcomes of the measurement, right? Okay, so if I have this matrix, if I write it down on a basis, for instance, in 2 dimensions, let's assume that it's possible to do this in 2 dimensions, right? Well, it should be possible, I'm not sure, but so let's do it in this way. I have a 2-dimensional space. I have a 4-dimensional. In this case, I have 4 complex numbers in essence, because this is a matrix that goes from a complex space to a complex space. So these can, in principle, be complex numbers. If this matrix is self-adjoint, in the matrix representation, this taking the adjoint is taking the transpose, and at the same time taking the complex conjugate of all the elements, right? So what I'm doing is I'm taking the complex conjugate of all the elements, A conjugate, B conjugate, C conjugate, and D conjugate, and then I take the transpose. So B turns into, here, taking the transpose, B turns into B transpose here. That is what, in the matrix representation, what taking a convex an adjoint is. So it's the conjugate of the transpose. If they are equal, what does that tell me about the numbers A? They are real. And D is real. So A and D are real. Yeah? So that is one thing. So I have 2 real numbers here. These guys here can be complex. So the off-diagonal elements can be complex. Right? How many real numbers do I need to specify such a matrix? So 2 here. And these guys can be complex. But I only need one of the 2, right? Because B is C conjugate and C conjugate is B. So this is, because of the symmetry, I only need 1 above the diagonal. And 1 complex is 2 reals. So I already had 2 reals here, and 1 complex here is 4 reals. So the space of the Hermitian matrices is 4-dimensional, in case my state space is 2-dimensional. In general, if my state space is n-dimensional, so if X is an n-dimensional Hilbert space, I will have an n-dimensional, a square matrix of dimension n. How many elements are on the diagonal? N. And they are real. How many off diagonal? Above the diagonal, because by symmetry, those are the only ones I have to specify. How many? 1 plus 2 plus 3 plus 4 plus 5 plus n minus 1. So 1/2 Gauss's formula. The sum of the first n minus 1 natural numbers. Complex, so 2 real numbers. What is this? N square. So in an n-dimensional space, the number of Hermitian matrices, or the Hermitian matrices, constitute a real vector space that is n square dimensional. Yeah? That is what I wrote here. The dimension of the Hilbert of the Hermitian space is the square of the dimension of the underlying Hilbert space. Right? So I have a real dimensional space. If this has dimension n, my Hilbert space, the option space that we will use later on, the space of all the uncertain rewards, will be n square dimensional, but will be a real Hilbert space. Okay? This is why I'm telling you this here. Okay, a few more things. That is eigenvalues. Because that is important in quantum mechanics, because, as I said, if I have a measurement that corresponds to a Hermitian operator, a self-adjoint operator, its eigenvalues are real, and they will be the possible outcomes of my measurement. They, and only they, will be obtained if I perform the measurement. Those are the only possible outcomes. So I have to tell you what an eigenvector and an eigenvalue is. So take any operator, any linear operator A, and let it work on the ket phi. Then phi will be an eigenvector if the action results in a multiple, in some multiple of phi. So in other words, if that is just multiplying phi with some real number, with some complex number in general, lambda, and that complex number in general will be called the eigenvalue of the operator A, or an eigenvalue. Right? If I take two eigenvectors with the same eigenvalue, phi 1 and phi 2, then A, let's say phi 1 plus, so lambda phi 1, I will do this, plus mu times phi 2, no, sorry, not lambda, mu. Mu 1 plus mu 2 times phi 2. So I let work A, sorry for this sloppiness. So this is mu 1 times this, and then I let A work on this. Right? Then, okay, so this is equal to bilinearity mu 1 times A times phi 1, so that is lambda times phi 1, plus mu 2 times lambda times phi 2. Okay, that is lambda times mu 1 phi 1 plus mu 2 phi 2. So this linear combination of these two eigenvectors is again an eigenvector with the same eigenvalue. This means that if I look at all the eigenvectors that correspond to a given eigenvalue lambda, they constitute a subspace. They are closed under linear combinations. They constitute a subspace. The subspace is called the eigenspace that corresponds to the lambda. So this is a subspace, and I will denote it by curly E lambda. So it's a subspace of the space, and all these vectors in there, in that subspace, are eigenvectors that correspond to the eigenvalue lambda. Okay? This is for general operators. What happens if these operators are Hermitian? If they are self-adjoint, you can prove, I'm not going to do it here, you can prove two very interesting things. First of all, that the eigenvalues are real. And this is important for measurements, because a measurement produces eigenvalues and we can only have real outcomes. I don't know of any measurements that produce a complex outcome. That would be a Nobel Prize in physics, I think. Right? So all the measurements have real outcomes, real numbers as outcomes. All the eigenvalues are real, and if I have two different eigenvalues, and I look at two eigenvectors that correspond to these two different eigenvalues, then they are orthogonal. Their inner product is 0. That's fairly easy to prove. I'm not going to do it here, but it's easy to prove. Look. Well, in fact, well, no, don't have time. Okay, so but accept this, please, right? But this is cool because this tells us that these eigenspaces that correspond to different eigenvalues are orthogonal to each other, right? So I can subdivide the entire space into orthogonal subspaces that are eigenspaces. That's really cool. Okay. So this also means that we can always find a basis that is orthonormal, or where the eigenvectors are mutually orthogonal and have norm 1, of eigenvectors of any Hermitian operator. You give me a Hermitian operator, I give you a basis of an orthogonal basis of eigenvectors of this operator, always. Yeah? As a consequence. We're nearly there. Okay? We still need to talk about projections. Yeah? What? Here? Or the previous slide? On the blackboard, yeah? I'm saying that these are two eigenvectors that have the same eigenvalue, right? So what I would try to prove here was that two eigenvectors with the same eigenvalue, that these constitute a subspace, that they are also, that the linear combination of these is also an eigenvector with the same eigenvalue. Okay? Sorry if I did that wasn't clear, sorry. Right, okay, so now, what is a projector or a projection operator? It's a Hermitian operator that only has two eigenvalues, 0 and 1. That is a projection. Right? We're nearly there. So in other words, if there are only two types of eigenvectors, the eigenvectors that are mapped, the vectors that are mapped to themselves, and the vectors that are mapped to 0. Those are the only possible eigenvectors. Right? Because the only eigenvalues are 0 and 1. So I have two orthogonal eigenspaces. The one that corresponds to 0, and that are all those are all the things that are mapped to 0. That is the kernel of that operator. And then the range of that operator is all the ones that are mapped to themselves. Right? That's also a subspace. And there is a famous theorem that says, in this case, that the space can always be, it's a special case, that this space is actually the orthogonal sum of these two spaces. The one that I project onto, so I have this space, the one that I project onto is this E1 space, and the one that is orthogonal to it is the ones that are all mapped to 0. Right? And that is the other one, the E0. And these are orthogonal because the matrix is Hermitian. And there are different eigenvalues. And eigenvectors with different eigenvalues are orthogonal. Okay. Now, take a normalized ket here. I claim that with this, I can associate a projection operator that I will denote like this. So, ket bra, not bra ket, but ket bra. And ket bra is a projection operator. Why? Well, let it work on any psi. So ket bra working on psi, what does it do? So let it work on psi. What I do here is I just take the inner product of psi and phi, and that gives me a real number that is multiplied by this ket. So I get a ket psi again, and this is the result. So I get the projection operator, right? It's either 0 or a multiple of that thing. This is, this is wrong, right? What was I doing? No, it's correct. It's right. It's correct. Yeah. So I get something that is proportional to phi. So I'm projecting onto phi. So I have one direction in space, and I'm projecting on that line. Yeah, so this is a one-dimensional projection operator. You can prove that it is. That's an easy exercise. I'm not going to do it. Prove that it is a projection operator, but you will need it later on. Okay. Let me. Yeah. There's one more thing I need to tell you here, and that is if I have a Hermitian operator, and I look at the quadratic form, that is, this is really crucially important. If I take a Hermitian operator, this is really cool. I can write this as a sum over all its eigenvalues, and this notation is the spectrum of A, and the spectrum is the set of all the eigenvalues. Right? So I call the spectrum of an operator the set of all its eigenvalues. So I have a finite number of eigenvalues, I have a finite sum here, so this operator is a finite sum of other operators, namely projection onto E lambda, this should be E lambda here. So you project onto the eigenspace and you multiply that projection with the eigenvalue. That is really cool. Any Hermitian operator can be written like this. Right? So it's like a mixture of any Hermitian operator is like a mixture, if you want, a convex combination. Oh, no, a linear combination of projection operators where the coefficients are the eigenvalues. And then, of course, if I take the quadratic form associated with this, I can take this, take the quadratic form, and for this you can prove that this is always non-negative. So this quadratic form here, associated with this Hermitian operator, we already know that it's always real. It's also a sum over all the eigenvalues of the eigenvalue multiplied by a non-negative number. Which means that this quadratic form will be non-negative everywhere if and only if the eigenvalues are non-negative everywhere. In that case, we call this operator, this Hermitian operator, positive semi-definite. So the positive semi-definite operators can be characterized in two ways. First of all, the associated quadratic form is everywhere non-negative. Whatever value I give it, it will always give a non-negative result. That's one characterization. An equivalent characterization is its eigenvalues are non-negative. That's two equivalent characterizations. Another way of writing this is that the minimum of the spectrum, so the smallest eigenvalue, is non-negative. Right? So spec of A is the spectrum of A, the set of all the eigenvalues. If I take its minimum, it must be non-negative. So this is the min spec is the smallest eigenvalue. So all the eigenvalues are non-negative if the smallest eigenvalue is non-negative, right? So if the minimum of the spectrum is non-negative. Which again means that A is positive semi-definite. And then one final thing, we're almost there. This is the last, I promise. But you need it. We need a density operator. Now, remember, we had Hermitian operators. Special Hermitian operators are the projection operators. These have only two eigenvalues, 0 and 1. What I'm now going to do is I'm going to take special linear combinations of these special projection operators. So I have a number of independent vectors in my space, phi1, phi2, phi3, phi4, linearly independent. The phi4 I couldn't have done in three-dimensional space, but okay. Right? So I have these three independent vectors, and I will use the projection operator onto these n axes. So these are n projection operators, and I take a convex combination of them. So I take a number of numbers, p1 through pn, that sum to 1 and are all positive. So I take a convex combination of these. Well, this is what we call a density operator. It corresponds to a probability distribution, if you want, right? So what you're saying, if you have this density operator, in a sense, is that my system is in either of these states with probability pk. So it's in the state pk, phi k with probability pk. That is what this thing represents, in a way. So this is Hermitian. Why? Because it's a linear combination of Hermitian operators, right? Hermitian operators constitute a linear space, so the sum of Hermitian operators is Hermitian. It is positive semi-definite, because the minimum of this thing, of the spectrum of this thing is non-negative. And the trace, that's another important thing for later. The trace is the sum of the eigenvalues. So any operator has eigenvalues. If I take their sum, that is what we call the trace. So the trace is actually equal to, well, if you look at this, if I look at the matrix representation of this, the p's will only be on the diagonal, clearly. And so the sum of the diagonal elements, which is also the sum of the eigenvalues, is equal to 1. So the trace is equal to 1. It is, so any operator, that's also the other way around, any operator whose trace is 1, and that is positive semi-definite, is a Hermitian, and is Hermitian, is a density operator. It's 1 to 1. Okay. Quantum mechanics, these density operators are really important. Okay, now we can go to quantum mechanics. How much time have I got left? Half an hour. Should be enough. So, I've already told you that if I have a system that is in a quantum state, in a certain state, then then the state will always be normalized. That is the idea. So a quantum state is a normalized element of the Hilbert space. So it's norm, or in other words, here the inner product of that ket with itself will be 1. So that is something that is one of the basic axioms of quantum mechanics. Another axiom of quantum mechanics says that if you perform a measurement on the system, you can associate with that measurement a Hermitian operator, and the possible outcomes of that measurement will be the eigenvalues of that operator. So the spectrum of that operator is a set of a finite number of real values, in this case, and those will be the possible outcomes of the experiment. If I do it, the system will give an outcome, and it cannot but give, these elements, which is why we call the system quantized. Right. So now it's time to go back to our theory. The idea in the theory is that we have options, and these options are uncertain outcomes. Well, so the x, in the classical case, the x is just a set of possible outcomes. And I'm uncertain here, I'm uncertain about which value I'm in. In the quantum case, my x is the set of all the possible states. And I don't know what state I'm in. I'm uncertain about the state of my system. This was a capital letter. I will also use a capital letter here. I will call this capital letter psi. So my unknown state is represented by a capital ket psi. I use a capital letter because I don't know it. And it belongs to the Hilbert space, the normalized Hilbert space. I don't know where it is. And on that system, so I'm uncertain about it. And now I'm going to look at what is the equivalent of a gamble. What is this uncertain reward? Well, the idea is if I perform a measurement on the system in this state, a measurement A, it will produce a number of possible outcomes, namely one of the eigenvalues of A. But I don't know which one. First of all, I don't know which one because I don't know where my state is. But also, I don't know which one because of quantum mechanics, right? I don't know what the outcome of the measurement will be. There is this uncertainty that is in quantum mechanics. I don't know. So what I see is that if I perform a measurement, I will get an outcome. And let's assume that you are now asked, okay, you know that the system is in a certain state, or you don't know, you think that it is in a certain state, or you don't know where the system is, in what state the system is. I will do a measurement on that system. I will use an operator A, and it will produce a measurement. It will produce an outcome, one of the eigenvalues. And you will get that reward. You will get that eigenvalue as a reward. You will get that outcome. You don't know what it is because of you don't know where the state is and because of quantum mechanics. Do you accept it? Do you think it's desirable, given what you know about the system? What? Sorry? It's not only that. Sure, it could be anything, right? If I have a system with a spin in this direction, and I measure along the other axis, I will have a negative spin that could give me a negative value. Right? So the measurement outcome will be either +1 or -1. Could be either of these two. And so, depending on where the state is and depending on quantum mechanics, you might. Yeah. If I know that my system is close to the up state, I will be pretty sure that my outcome will be in the up state, and then I will accept the gamble. If I'm pretty sure that the system is in the down state and I prefer the up measurement, then I won't accept the gamble or the measurement in that sense. So my uncertain reward in this is just a measurement because it produces an uncertain outcome. So my option space U is the set of all the measurements. I have an option space. They are the measurements. And ask you, do you accept? Which measurements do you accept? What do I need? More. I need a unit. This is fairly easy. I will take as a unit, the unit measurement, the identity operator. The thing that surely gives me 1. Right? If I perform a measurement with this operator, it will always give me 1. 1 times, because I of the identity operator acting on any phi gives me phi. So the only eigenvalue of the identity operator is 1. And since the measurement produces an eigenvalue, it must be 1. I can only get 1 from this. So this is the certain outcome 1. So this will be my unit. 1 H is my unit measurement. So I have a unit. I need a topology. On this space, I need an inner product. It's a finite dimensional space, right? It's a finite dimensional linear space. It has dimension n square. Finite dimensional, I can take any norm. They're all equivalent. They all give the same topology. Let me take this one. The trace of A times B is AB. That is a good inner product. It's called the Frobenius inner product. So I multiply A with B, and I take the trace of the result. That is an inner product. It's called the Frobenius inner product. Yeah. No, I'm uncertain about the state, but the outcomes, the uncertain rewards, are not states. Yeah? Yeah, well. So this is the idea. Suppose that I have this one typical system is a qubit. It can be, let's say, in an up state or a down state. That is typically what can be in many states and combinations. So the spin can be can be up or down, let's say. If I perform the measurement, so this is the z direction. If I perform a measurement of the spin in the z direction, it will give me 2 possible outcomes, 0 and 1 or -1. Right? And that will be the result of these 2 outcomes, more or less. Okay? I don't know which one it will be, right? This is why I said, if I have a state that is close to this one, then I'm pretty sure that the outcome will be 1. If I have a state that corresponds to this one, I'm pretty sure that the outcome will be -1, and then I will not accept it, typically. So this is why, given my information about where the state is, and given quantum mechanics, where I don't know what the possible outcomes will be, given that, maybe there's something else that I should tell you that I haven't told you yet. I'm sorry. That is that if I do a measurement on a system, phi, where phi is already in the eigenspace corresponding to an eigenvalue, so if phi is in that eigenspace, if I have prepared my system in such a way that I'm already in the eigenspace of such an operator, then the outcome will surely be lambda. That is another thing that we know from quantum mechanics. That's one of the other axioms that I forgot to tell you, right? So I have a system in an eigenstate, I perform a measurement on that system, then the result will be that eigenvalue. This is why if I know that, if I'm pretty sure that my system will be in a state that corresponds to an up spin, and I measure the spin, then I'm sure that the outcome will be this one. And since this is a plus, I will accept the outcome. If I'm sure that the state corresponds to this, I will get a negative outcome almost for sure, and then I will not accept it. Yeah, so that is the idea. Is that clearer now? Okay, yeah, fine. Okay, so but we're still trying to find an option space, right? So I have an inner product. That inner product corresponds to a norm. Take the inner product with itself. That gives me a norm. Right, so the inner product of A with itself, and if they get the square root, that satisfies all the properties of a norm. So I have a norm, I have a topology on my option space. Good. I have a unit. Good. What else do I need? I need a background. So I'm, again, going to try and derive, or you are, if you want, going to try and derive a background. Background is a strict vector ordering on this space of Hermitian operators. That represents complete ignorance. The exercise could be, you are now looking for a convex cone in that space of gambles that, or measurements that you will accept, definitely will accept, if you're completely ignorant. Or will desire if you're completely ignorant. What is it? And the idea is it's really, essentially, mutatis mutandis, as we say, the same argument as in classical probability. Right? So my question for you is now, do you want to do it, or do you want me to do it? You can choose. You are free agents. I'm perfectly happy to do it for you, but if you think this would be a wonderful exercise, then I'm perfectly happy to let you do it as well. So which is it going to be, boys? Yes or no? Given your level of activity at this point, I'm getting the impression that you'd rather have me do it. Is that a correct impression? What? Maybe you, yeah, try guessing the answer. So remember, in the classical case, what we had was, we have a set of accepted gambles, a set of rejected gambles. A set of desirable gambles are the ones that I accept and don't want to give away. And the symmetrical gambles, indifferent gambles are the ones that I accept and that I want to give away. So, what do you think? Is A going to be? So we had, in the classical case, we had that after all these arguments, we knew that A was going to be the set of all the gambles for which the infimum of this f is greater than 0. So what it's going to be now? Doing the same type of argument, right? So suppose I have a constant measurement whose outcome is guaranteed to be non-negative. So if I have mu times I, so the measurement that definitely gives me mu, whatever happens, and this mu is non-negative, I will accept it, because I will get mu, and it's non-negative, so I will accept it. And therefore, and now, so this one, and so if mu is greater than 0, then this will be an A. All right. Now, the other argument was, if I have a gamble that is above a mu, definitely, surely above a mu, that is non-negative, then I will also accept it. What is the equivalent of being above, certainly above a mu? When does that happen? I have a measurement, A. What are its possible outcomes? The spectrum, right? Those are the possible outcomes of that measurement. This is what you could get if you do it. When is this certainly going to be above a mu? When does it, the outcome that you get is definitely, certainly going to be above mu. When? Minimum of that spectrum is greater than u. So, sorry. All the measurements for which the minimum of the spectrum is non-negative, you're going to accept. Same argument. Because this can only give non-negative measurements, and therefore you'll accept it. Right? Same for R. Any measurement for which the maximum of the spectrum is smaller than some negative number, in other words, smaller than 0, you're going to reject. Why? Because what you get will definitely be smaller than 0. Whatever you get will definitely be smaller than 0, and therefore you should reject it. So what I'm beginning to suspect is that the infimum of f plays the role of the minimum of the spectrum, and that the supremum of f plays the role of the maximum of the spectrum of A. And therefore, I can repeat the entire argument, and wherever I see infimum of f, I write minimum of spectrum, and wherever I see supremum of f, I write I'll give you the form of the complete ignorance criterion. If I accept A, and the spectrum of B is included in the spectrum of A, then I must also accept B. That is the complete ignorance equivalent, right? And if I do that, then I find same argument as before. The only thing you have to do is replace the minimum of the infimum with the minimum of the spectrum and the supremum with the maximum of the spectrum. You will find that the only indifferent measurements in complete ignorance are the 0 measurement, and this is the constraints that you have on the desirable measurements. And if you work in the desirability framework, there's only one that's going to remain, and that's this one. The positive cone, the background cone, is the cone of all measurements where the minimum of the spectrum is non-negative and that are themselves not 0. So all the positive semi-definite measurements that are non-zero. This is where positive semi-definiteness comes in. The background is just the positive semi-definite measurements. This is why I needed positive semi-definiteness, whose eigenvalues are not all of them, not all of them 0. Positive or non-negative, but not all of them 0. Those are the desirable ones. And so the background ordering is this. Okay, I found the background ordering from arguments that I can now make physical. Why? Because this argument here, this one, the one with complete ignorance, that criterion, in the classical case, I could say this is a set that is invariant under all the permutation, all the transformations of the space X, of my possibility space. You can have a similar argument here that turns to physics. That is, this is invariant under all the reasonable transformations of the state space. So if I know nothing, that whatever I do with the state space will have no effect. And that is a physical requirement. It tells us something about the physics of the problem. Right? Tells me that complete ignorance means that I can do whatever I want with the state space. And it will not change my beliefs. Not affect them crucially. So I have a physical and an epistemic argument, if you want, to take this as the background space. So now I have a background. We have everything to do a theory of desirable measurements. Right? So gambles become measurements. I have a theory of desirable measurements. These are convex cones in this Hilbert space that always include the background. So desirability is clear. Now we're going to look at Archimedeanity. We're going to look at the lower provisions, the coherent lower provisions. But these coherent lower provisions are lower envelopes of coherent provisions. So if I know the coherent provisions, I'm okay. Because the lower ones will just be lower envelopes. So I can completely characterize the lower provisions if I can the lower provisions if I can characterize the provisions. So just as in the classical case, I would now like to ask you, what do these coherent provisions look like? So they are, going to clean the blackboard, they are linear. That's not a problem, right? The linearity is not a problem, but what makes them coherent provisions is this background. So let's find out what these coherent provisions are, given that we now know what the background must be. Okay. Let's see. So a coherent provision, I know that it's linear, right? So I know that P of lambda times A plus mu times B must be equal to lambda P of A plus mu P of B. That is trivial, it's linear. The only thing that I now must do is somehow get in the background. Right, but there's something I know already. And this is Ries's representation theorem in linear spaces that tells me that any linear operator, any linear functional, can be written as a bra. Well, no, not as a bra, sorry, but as a dual linear operator. So in the sense, I know that for every P there is some measurement BP, so some Hermitian operator BP, such that P of A is equal to the inner product of BP and A, for all A. This is Ries's representation theorem. If I have a continuous linear operator, I can always write it as an inner product of some vector, constant vector, with the argument. Right? That is a theorem that I give you. The only thing that we have to do then, so this is also, let me see, this is also the trace, remember, of BP times A. The Kronecker, the Frobenius product. Sorry. Hermitian operator. Sorry, I'm getting tired. Yeah, so the idea is we now have to find this BP. So given a P, a linear operator P, I have to find a BP such that for the P that I have, it must look like this. Okay. This is the equivalent of what we had for gambles, namely that any P of F is actually equal to the expectation operator of F for some vector P, and then I use the background to show that P must be a mass function. Right? Now I have this BP, which is the equivalent to my mass function, but I still must prove that it is use the background to prove that this is this. So this P here, which by the way, I could always write as an inner product between P and F, right? I could also do this, or some inner product between P and F. Right? So I'm doing the same here. So I'm looking at I need to find this one, or at least use the background to impose constraints on this one. What are the constraints? Well, I know that P of A is greater than or equal to the infimum of A. What is the infimum? Minimum of the spectrum. So this is greater than the minimum of the spectrum of A, and therefore, if I go to negative things, so smaller than the maximum of the spectrum. So the provision always lies between the smallest and the largest eigenvalue. Okay. That's one thing I know. Okay. So I know that the trace of BPA must lie between these two things. Now choose two different A's. First one, the unit. P of the unit. What are the eigenvalues of the unit? 1. So the minimum is 1. The maximum is 1. P of the unit must be 1. Okay? So the trace of BP times the unit, which is BP, must be 1. What else? Take as A projection operator. For instance, project it onto phi. This is my A now, right? So P of this projection must lie between the minimum of the spectrum and the maximum of the spectrum. What is the spectrum of a projection operator? 0 and 1. Minimum is 0. Must be between 0 and 1. Okay, I also know that it is the trace of BP times phi times phi. So this lies between 0 and 1. Okay. There is a curious property of the trace operator that I haven't mentioned yet, and that is what we call the circularity condition, if you want. That is, I can turn these operators around in a circle, and it doesn't affect the trace. So what I'm going to do is I'm going to move this operator here, and that doesn't affect the trace. So this is the trace of phi working on BP, working on phi. Yeah? But this is a real number. This is a 1-by-1 matrix, so the trace is the real number. Right? So this is equal to phi BP phi. And this must be between 0 and 1, so definitely non-negative, for every phi. That tells me that my BP is not only Hermitian, but positive semi-definite. So what have I found? I have found that BP is Hermitian, it's positive semi-definite, that's my notation, and its trace is equal to 1. That's what I can deduce from the background ordering. What is an operator that satisfies these three conditions? How have I called it? Have you paid attention? A density operator, right? So what I know is that a coherent provision can always be written. There's always one unique, by the way, because Ries says that this is unique. For every coherent provision, there is a unique density operator rho, such that the probability, or the provision rather, of A is equal to the trace of rho times A. And this is Born's rule. We have derived the basic probabilistic probability equation that there is in quantum mechanics from the background ordering and the linearity. So the background is enough to get to this. And the background follows from a simple physical argument. So the message. First of all, probability theory in the form that we don't know it, or that you didn't know it before you came, in the form of desirability, which is a deductive inference system. It's based on, it has its own way of deduction. Provided that we allow for partial specification, provided that we allow for imprecise probabilities, then we can turn probability into a deductive inference system. First conclusion. Second conclusion, probability itself, what we call probability, is actually nothing but linearity and background. Once we have that, we have probability. Third one, the difference between classical and quantum probability lies only in the background ordering. Why? Well, in both cases, I have a real linear space, right? The one is n-dimensional, the other one is only n-square dimensional, so I don't have all of them. But it's a real linear space, and what is a probability on that linear space will be different in the case of quantum mechanics and in the case of classical probability, precisely because in those cases the background is different. And why is the background different? Because of physics. Because of simple arguments that you can make physical. So the connection between classical and quantum probability is actually very deeply rooted into this formalism. And once you see it, it stares you in the face, right? But you have to see it. You will never again unsee this, right? I've given you nightmares. Right. And then one more thing, and this is like the cherry on the cake, right? So when we work with sets of desirable measurements, we work with measurements, and in quantum mechanics that is called the Heisenberg picture, right? People working with measurements saying that whatever you do can be done with measurements, then you are working in the idea that Heisenberg had in the beginning. If, on the other hand, you work with, working with sets of measurements is, in a sense, working with measurements, and then you are in the Heisenberg picture. On the other hand, if you work with density operators are just convex combinations of precise states, of wave functions, if you want. So what you do here is essentially you work with wave functions, with states, and you work in the Heisenberg picture. Right? So Heisenberg, again, the fact that these are almost equivalent in the sense that desirability is a bit more general than working with density operators tells you that in this context, if you work with desirability, the Heisenberg picture is a bit more powerful, marginally more powerful, if you want, than the Schrödinger picture. Right? And I'm done. And you are done. Ah, yeah, my project. So what I'm going to do is what I haven't talked about yet is conditioning. Right? So you can do conditioning in this abstract space. And then you can have this general theory, and then you can say, okay, I'm going to now look at the classical case, and you will get a theory of conditioning, which gives you Bayes' rule. And then you can do the same argument in quantum space, the same argument, mutatis mutandis, and you will get something. Yeah, what will you get? That is the project. Okay?